All right. Hello, class. Mr. P here. Um, I am streaming. Oh, wait a second. Let me just make sure I'm okay. I'm live. Hello, class. Mr. P here. Um, Today's a Monday. We don't have school today. And I'm actually going to be taking tomorrow off in order to finish writing your final exams. So, for that reason, I'm pre recording your lesson. Okay. And you are going to watch this lesson during the class time, during the class time, and you will submit attendance like you normally do. Okay. If you do not submit attendance, there's going to be no substitute teacher or anything. Okay. So if you do not submit attendance, you will be marked as absent. And maybe your parents will get a phone call from the school that says such and such was absent. And then your parents, are going to email the school and they're going to say, but such and such says they were there. And when they do that, I'm going to say, no, they weren't there. And I'm going to hold the line and you will be absent and it will be on your permanent record for the rest of your life that you were absent on January 20th, 2021. Ha ha ha, for physics class. Okay? And your life will be ruined. It's not going to be ruined. Okay? I think the idea of throwing a fuss over attendance is ridiculous, but it is something that I have to deal with continuously, and it really makes me mad. All right, so as I said last week, this is there's going to be no new content this week. My hope is that you will use this week to get caught up on any missing assignments and prepare for the final exam. Okay? All right. So I'm going to be reviewing. I'm just going to go rapid fire through content from the very beginning of the school year. And I'm going to see how far I can get in a half an hour because that's how long class is tomorrow. Okay. Remember to fill out attendance right now. Okay, so let me switch over. So the first thing we talked about in this class was kinematics. By the way, this is really, if I were you, I would have a sheet of paper that just says physics equations, and I'm basically going to give you the highlights of all the important equations, okay? So for kinematics, we had this thing called the position vector, which is a function of time. And it's a vector, so it has an I component and a j component. And the x component is your x coordinate as a function of time. And your j component is your y coordinate as a function of time. Okay? If we take the derivative of that, we get the velocity. So it is the derivative of the position vector as a function of time. Okay. If we take the magnitude of the velocity vector, that's going to give us the speed. Okay. Now remember, when we take the magnitude with these vertical bars, all right, putting those vertical bars means do the Pythagorean theorem. Okay. If we take the derivative again, we get the acceleration as a function of time. All right. So that is going to be dv dt. All right. We talked about one-dimensional motion. where the acceleration is constant. And when we did that, we derived what are called the kinematics equations. So this is an important point. The acceleration is constant. In that case, x of t is equal to x naught plus v naught t plus 1/2 at squared. Taking the derivative of that equation gives us the velocity as a function of time is v naught plus acceleration times time. And there's also a third equation which comes from combining these two equations, which tells us that v final squared equals v initial squared plus 2a delta x. By the way, we can express these relationships in terms of graphically. So if you have a position time graph, then the slope of that is going to be the velocity, and if it's bendy, that is acceleration. So that comes from these definitions, and interpreting them in terms of calculus. And then if we have a velocity time graph, the slope is acceleration, and the area under the curve is the displacement. Okay? We talked a little bit about projectile motion. So for projectile motion, we have an initial launch speed, which I called v naught, and we have an initial launch angle, theta. Okay. So the vertical component of that initial launch, that initial velocity vector is called v y naught, and it's equal to v naught sine of theta. The initial horizontal component of the velocity is called v x naught, and it's equal to v naught cosine of theta. All right? And so this gives us the equations of projectile motion. So there's an equation for x as a function of time. And because projectile motion is two-dimensional, we also have an equation for y as a function of time. Okay? The x as a function of time is x naught plus excuse me, v naught cosine of theta times t. And this one is y naught plus v naught sine of theta times t minus 1/2 gt squared. So g is the acceleration due to gravity, which of course is 10 meters per second squared if we're talking about Earth. Okay? And of course, we also talked about what is called the trajectory, which is y as a function of x. So height as a function of position, not as a function of time. And that is going to be equal to tangent of theta, well, I guess it should be y initial, plus tangent of theta times x minus g over 2 v naught squared cosine squared of theta times x squared. So that's your trajectory. So what were the tricky types of problems? I'm not going to do any examples just in the interest of time, but the tricky example problems that we did in class, just to refresh your memory, we did multi-step problems. So those are problems where the acceleration is changing and the position and velocity at the end of one step is going to be the position and the velocity at the beginning of the subsequent step. Okay. We also did problems with multiple projectiles. All right. So if you need some review on that stuff, I would recommend going into the schedule and figuring out the dates where I covered that, and then find those YouTube lessons. Okay. Boom. So there's kinematics. Let's move on to forces. If you recall, a force is a push or a pull. Okay. And so we denote a force by F. And if you have a force that's diagonal at an angle, well, force is a vector. So that force is completely equivalent to a vertical force, which is going to be F sine of theta, and a horizontal force, which is F cosine of theta. So that's really useful. Whenever we have a diagonal force, we probably would want to break it up into its equivalent of a vertical force and a horizontal force. That just makes problems easier most of the time. There are a number of forces that we considered. So in particular, we considered applied forces, which are F, just denoted by F sub A. We considered the weight force, which is the force due to gravity, and that's minus mg. We considered the tension force, which is the force from a rope, F sub t. We considered the normal force, which is denoted by F sub n. That's the force from a wall, okay? Or any two surfaces that come into contact with each other, that's a normal force. We considered the elastic force, which is minus kx, where k is the stiffness and x is the amount that the elastic thing is stretched. We considered friction, okay, which there were two types. There was static friction and there was kinetic friction. Static friction has a maximum value given by mu sub s times normal. Mu sub s is called the coefficient of static friction. And then the kinetic friction is equal to mu sub k times normal. So when do you have static friction? When do you have kinetic friction? Well, static friction is there when you have two surfaces that are not sliding across each other. Kinetic friction is there when they are sliding. And lastly, we talked about drag force, which is F sub d, and it's equal to minus a constant times the velocity. So it points in the opposite direction of the velocity. It's an oppositional force. So these are some of the forces that you encounter. Now, once you've encountered those forces, we have some laws for how do the forces result in motion. One of the examples, one of those laws, is Newton's second law of motion, which says that the net force as a vector is equal to mass times the acceleration vector. So we can use this to calculate the acceleration and then do kinematics. All right. And the other one is Newton's third law, which describes interacting systems, which says the force of A on B is going to be equal to the force of B on A. All right. So we basically use this to solve problems, and I think I will go do a couple of examples here, just for the new stuff. So what were the new types of problems that went beyond what we discussed in the first year of physics? Well, one of them was a multi-part system. Okay, a system that has more than one piece. So let me just give an example of that. Maybe we've got something like 2 blocks, okay? And the blocks have an applied force. The applied force is horizontal. This block has a mass m1, that block has a mass m2. And each of these blocks has a different coefficient of friction. Okay, so this one has a coefficient of friction mu1. This one has a coefficient of friction mu2. All right. So if I were to do a free body diagram of each of these blocks, okay, well, if I look at the left block, it's got the applied force going to the right. It's got, and we're going to assume that it's sliding. Okay, so we've got kinetic friction on block 1 going to the left. And then also it's being pushed by the block in front of it. The block in front of it is pushing it backwards. So I'll call that normal force between the blocks, N sub BB. All right. There's a normal force from the floor on object 1. And then there's a weight force going down. All right. If we look at the front block does not experience the applied force. The applied force is only on going to be on block 1. So what is pushing block 2 forward? Well, it's the normal force between the blocks. And by Newton's third law, these two forces are action and reaction, so they have to have the same size. All right. And then there's a force slowing it down, which is the friction on block 2. Okay, so we have F sub k on block 2. There is a normal force that's on from the floor on block 2, and then there's a weight force, okay, on block 2. So because these blocks aren't moving vertically, the vertical forces have to balance. So this force has to balance that force, and this force has to balance that force. All right? So what that means is that the normal force is going to be equal to the weight because it's a flat surface. And that's going to allow us to calculate the kinetic friction. Okay? If we were to do horizontal Newton's second law for this first block, it would be F sub A minus F sub kinetic friction on block 1 minus normal force between the blocks equals M1A. Okay? And then we have, for this one, we have normal force between the blocks minus F sub k on the second one equals M2A. Now they have the same acceleration because these two blocks are pushed against each other. They're sliding together. All right. So we could use this to solve for n sub bb and the acceleration. Okay, so that's called a multi-part system. The other new type of problem we did was the terminal velocity problem. So we have an object that is falling. It's got the weight force going down. It's got the drag force going up. Okay, so if we do net force equals ma, the equation, well, ma is actually m dv dt. All right. And the net force is going to be minus CV, that's the drag force, minus mg. All right. So this is called a differential equation because it has an equation for a function and for that function's derivative. So you can't solve this by algebra. Generally speaking, the best way to solve a differential equation is to guess and check, but there are a few methods of solving it, but they're just tough to solve in general. This one is about as simple as they come, and so you can use it to solve for the velocity as a function of time. And what we get is minus mg over c plus v naught plus mg over c times e to the minus ct over m. Okay? So basically what happens is after a long time, this is e to a negative number, so as t goes to infinity, this exponential term goes to 0. So the velocity goes to minus mg over c. And so mg over c is called the terminal speed. Okay? Let's talk about energy. See if I can talk about energy really quickly. So we started off by defining potential energy, U of x. And potential energy is a function such that minus du dx is equal to the force at a given position. Okay, so it's equivalently, you could think about the potential energy is minus the integral of the force with respect to position. Okay. Then we can go ahead and define kinetic energy. Okay. So defining the kinetic energy, K is 1/2 mv squared. All right. And then we can define the total energy as E equals K plus U. And when you do that, we proved that dE dt is 0, which means that energy is conserved. Some of the common forms of potential energy are gravitational potential energy, mgy, and elastic potential energy, 1/2 kx squared. All right. We discussed U of x graphs. So if you have a graph of potential energy as a function of position, then the particle is going to be, and you have a total amount of energy E, the particle is going to be confined to the region where the potential energy is less than the kinetic energy. So it's confined to that region. All right. The vertical distance between the amount of energy and the amount of potential energy is the kinetic energy. And similarly, if we think about a ball on a hill, the direction that the ball would roll is the direction of the force. Okay. If you, I'm trying to think here. So that's pretty much what we talked about in terms of energy. Oh, I guess I could talk about power or work. Let's talk about work. Work is equal to a transfer of energy between systems. Okay. And the work is equal to the integral of the force. Okay. With respect to position. We could also think about it as the area under the curve of a force position graph. Is work. And then, of course, power, P, is equal to the rate at which work is done. So it's the derivative of the work with respect to time. And that ends up being the dot product of the force with the velocity of the particle. Okay? So I think I'll stop there. So I once again want to remind you to fill out attendance. You will be marked absent no matter what your parent sends to the attendance office afterwards once you forget. And furthermore, I want to remind you to please get caught up if you're behind. This is your chance to get caught up. There won't be another chance. I really don't want to give anyone a bad grade this semester, especially given the circumstances of what's going on in the world. So I will see you guys on Thursday.